Right, and it's rates of reaction time. This is quite a nice little thing. No equations. It's nice. It's nice. Right, here we are then. We're speeding up the rate of a reaction, and there are different ways of doing it. So I've just shown it pictorially to begin with. So if we wanted to cook a carrot and we wanted it quicker, we'd chop it up. That's about surface area. If we want to do some washing, we want to speed it up, we'd add some enzymes. Here, biological washing powder. Here, if I put these in some water, it would fizz a bit. Do I want it to do more? Yeah, put more in, have more concentration. This is not doing much. What should I do? Heat it up, add some heat. Okay, fabulous. So the first we're going to start with is temperature. Now, the effect of temperature on the rate of reaction can be measured in many ways. This is one way, and this is where you've got your conical flask and you place in it some sodium thiosulfate and some hydrochloric acid. You heat it up to the temperature that you wish and you place it on a cross. You then have a look down at the conical flask and you see how long it takes for this cross to disappear. Now, it doesn't actually disappear, I'm sorry to say. What's actually happening is that within the reaction we are forming a precipitate. That's a solid formed between these liquids. So inside there's this solid sulfur forming, which makes the whole thing go cloudy, and you can't see the cross anymore, so it looks like it's disappeared. Sorry, no magic in our science lessons, I'm afraid. So you do that at different temperatures and plot it on a graph. Now, this is what it would look like. The temperature down here, so if I've started about 0 here or whatever, I would be very long time for that cross to disappear, probably minutes really, where there'd be about 5,000 up here. And as I increase the temperature, the quicker and the quicker and quicker and quicker and quicker and quicker it would go. And here's a beautiful graphic to explain that. Right, fab. So if I describe that graph, I'd say as the temperature increases, the time taken for the cross to disappear also increases. Great. Here's another way of showing the effect of temperature. Here, this reaction, a different one, mind you, is looking at the time and looking at the volume of gas produced over time. And they've plotted on it what happens to a reaction when it is 25 degrees. Now, if it was 35 degrees, you would expect it to go faster. Oh my goodness, this is the, right, let's pretend we've done that bit. So it's going to go faster. Oh. Okay, so it goes faster, much faster, but it also stops at the same point, because it stops when all the reactants have reacted, and that's going to happen at the same point with whatever temperature you use. Because you can't suddenly have more reactants. So let's say that's actually, let's say it's 55 degrees C. Okay, so now your job is to explain why. So to describe it, you just go as the time increases, volume of gas increases. If you compare it to 55 degrees, the volume of gas increases much faster. And they stop at the same point because both of the reactants have been used up. Fab. Why then? Oh, hang on. So why this happens is we've got, I'm going to demonstrate with this box of matches and a match. Now, if I led them side by side, so I'm not giving them any energy, I'm not moving them about, they're not going to do anything. This match here is just going to sit there nicely, lying in the sun, maybe. And if I give it some more energy, they will wobble about. Wobble, 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 wobble. And now and again, the match might hit the matchbox. But it's not going to do anything because it's not really hitting it very hard. So if I give it even more energy, it's more likely to collide and collide with more energy, enough energy to cause it to light. Now hang on, no expense spared here. Hang on, wait. Hey, look at that. Okay, so now it's lit. So what's happened is I've given it heat energy, which it's converted in kinetic energy, so it's moving about faster. Therefore, they are more likely to collide, okay, more likely to collide, that's important. And with enough energy to react. And we call that energy activation energy. So the more heat you give it, the faster they move, the more likely they are to collide, and with enough energy to react. That energy is activation energy. And if that's a mouthful, you can just say the more likely they are to collide successfully, and that covers all the activation energy bit. So that's about temperature.